Okay, we're talking about powers and powers of 10 in scientific notation. This is lesson 4.7. So if we consider powers of 10, notice that 10 to the third power is 1,000. Remember, that's just 10 times 10 times 10, so you end up with 3 zeros there. And then 10 to the second is 10 times 10, is 100. And notice that as you go down the scale here, that each number is 1/10 of the previous number. So 100 is 1/10 of 1,000, 10 is 1/10 of 100, 1 is 1/10 of 10, and so on. And as I move down into the negative exponent zone, then I would get 10 to the negative first has to be 1/10 of 1, which is just 1/10. And we also know that equals 1 over 10 to the first, when we studied the negative exponents property. 10 to the negative second is 1/10 of 1/10, which is 1/100th, which we also know is 1 over 10 to the second. And finally, 10 to the negative third, we could keep going like this, is 1/10 of 1/100th, which is 1/1000th, or 1 over 10 to the third. So let's remember that as we're considering these problems. A lot with word problems to gain an understanding of these concepts. So let's look at this first example, the word problem. There are 4 million bytes of memory and 4 gigabytes of RAM. Write this number using a power of 10. So we're trying to write the 4 million bytes of memory in scientific notation. So, I'm sorry, as a power of 10. So I'll just rewrite the number really quickly. And we know that this really means 4 times 1 million. And 1 million says 6 zeros is 10 to the 6th power. All right, so that's what we would want to say using a power of 10. That's also going to end up being what it is in scientific notation, but we haven't talked about that yet. So 4 times 10 to the 6 bytes, that's how we would write that number using a power of 10. So this next problem, you have a bookstore that has 40,000 books on its shelves. An online bookseller has 30 million books available. About how many times greater is the number of books online than the number of books in the store? So that's really a ratio problem. So you have 30 million over 40,000. And if we rewrite those with powers of 10, it becomes an easy problem to solve. So 30 million is actually equal to 3 times 10 to the 7th power. 40,000 is equal to 4 times 10 to the 4th power. We can subtract the exponents there. Treat this like two different fractions, really. So it's 3/4 times, if I go 10 to the 7 minus 4, and I get 3/4 times 10 to the 3rd power, right? So it's that many times greater. We could say 0.75. I guess we could leave our answer. So this is 0.75 times 1,000. And since we know what that is, we would say that it is 750 times. The online number of books is 750 times the number of books that they have in the bookstore. So this next problem, you have a housefly weighs 0.002 pounds, or of a pound. So that's 10 hundred-thousandths, 2 10,000ths of a pound. A dime weighs 10 hundred-thousandths, 5 1,000ths of a pound. How many times greater is the weight of the dime than the weight of the housefly? Well, the housefly, we're going to call that 2 times Now to move my decimal one to the left, I need to go to negative, but I need to move my decimal. So let's see what's going on with this 2 to get there. I need to move it once, twice, 3 times, 4 times. So that's going to mean what I have here is 2 times 10 to the negative 4th. That's the number of pounds. I mean, it's a fraction of a pound for the housefly. Now the dime weighs, so that is, let me get the number so you can see it. That's a 5. So it's 5 times 10 to the something. So what is that? So let's put our decimal right here, and we need to move it once, twice, 3 times, and that's where our decimal is in the number we're given. So that's going to be 5 times 10 to the negative 3rd. Now it says how many times greater is the weight of the dime to the weight of the housefly. So we'll put the weight of the dime on top in this ratio. And notice that this is 5 halves times 10 to the negative 3 minus negative 4. So that's negative 3 plus 4. So that's going to be, so that's going to be 2.5 times 10 to the first. So that's just going to be 25 times. All right, so let's go to the next. So now let's talk specifically about scientific notation. So scientific notation is a shorthand we typically use to express so it's very large and or very small numbers. So it's a shorthand to use to express very large or small numbers so that we don't have to write out all the zeros. Now, so how does scientific notation work? Well, you have, let me just write this. This looks like a check mark, but that's actually a C. That's just a generic number, and that's an N. So a number in scientific notation is written in scientific notation. It has the form C times 10 to the 9th, where C is a number that is greater than or equal to 1, but less than 10. All right, so let's go to the next page and see how this works. So let's look at some examples. Now, and so if we're going to take this to product form, what that means is just figure out what it is times some multiple of 10. So I'm going to make this 7.25. So to do that, I moved the decimal over 5 places. So that would be times 1 and 5 zeros. So that's called product form. And then I'm just going to say what that 10 to that 100,000 is. That is 10 to the 5th power, just counting the number of zeros. Now, with small numbers, it works the opposite. I'm going to make this 6 times so just going to replace the 6 with a 1 here, so I'm going to have the same number of zeros. One more 0. And so what is this in terms of a power of 10? Well, what I'm doing here is I'm multiplying so every time I move my decimal place over, that's going to be a -1 in my power of 10. So 1, 2, 3, 4, 5, 6. So I'm going to say 6 times 10 to the -6. Now let's check that just to make sure we got it right. So if I have 6 and I want that number to be what I started with here, I'm going to go over 1, 2, 3, 4, 5, 6. Put one more 0 there, so that looks right. So 6 times 10 to the -6. Now, just changing things up a little bit, let's see if we have the product form, what would that be in standard form? Well, I'm just going to slide the decimal to the right here, 5 places accounting for those zeros, so it'd be 41, and not 4 zeros because I've already moved it over 1, but 3 more zeros. So that'd be 41,000. Now, over here, this is going to be 4.1, and I can count the number of zeros I have, which is 4, 10 to the 4th power. Now, 7.23 times 10 to the, times 0 and I've got 6 zeros before the 1. All right, so what I'm going to do is, it might be easier for me to put this in scientific notation first. So to move this decimal to the other side of the 1, I've got to go 1, 2, 3, 4, 5, 6, 7. So this would be 7.23 times 10 to the -7th. So rewriting that over here, I'm going to have 7.23, and I'm going to, actually let me slide that over just a little bit. So just rewriting that over here before I put it in the box, I'm going to move this over 7 times. 1, 2, 3, 4, 5, 6, 7. So I'll have 6 zeros after the decimal place. So let me rewrite that. 0 point, now 6 zeros after the decimal place, not 7, because I had to move to the other side of the 7 first. So that's what it would be. Now, standard form is 3,050,000,000, all right? So I'm going to rewrite this as 3.05, and how many places do I have to move it? So if I move the decimal over 369, that's going to be times 1 billion, and so, and over here this would be 3.05 times 10 to the 9th power. A little bit easier with positive numbers. Now let's look at this last example on this page. I've got 9.2 times 10 to the -4th. I think this might be easier to start over here and go 9.2. I need to move this 4 places that way. So 1, 2, 3, 4, and put zeros there. So my answer here is, for standard form, is 00092. And so in terms of product form, I'm going to be 9.2, and then, so the way I'd kind of do this one is I'd put a 9.2 up here, like so, and I want to move that, so I'm going to move a decimal place once, twice, 3 times, 4 times to get that 0. So down here I've got a 1,000.0. So let me see if I can rewrite that. I'm going to have 3 zeros before the 1. All right. So my final answer here will be and that would all equate with all 3 versions. So let's say we have the average distance Mars is from the Sun is 141,600,000 miles. Write this in scientific notation. All right, that's pretty straightforward. So let's write the number. So I'm going to write it 1.416. Now where's my decimal when I need to move it? So it's going to be times 10 to the positive something. So I'm moving it 3, 6, 8 places there. So that's going to mean this is 1.416 times 10 to the 8th. Again, include your units. Now, the diameter of a 1/4 ounce gold American coin, so remember diameter it's this distance across. This would be the diameter, right? It says it's 0.2022 meters, because meters, like a little less than a yard, so it's a fraction of a meter. So write this number in scientific notation. So I've got 0.022. I want to move the decimal place to there. So if this number that I'm making that's multiplied by my power of 10, by the way, that's called the mantissa, I'm going to make that 2.2. So, and since I'm expressing a number less than 1, we know we're dealing with a negative exponent. Since I moved that decimal place 2 places, I am going to put a -2 there, and that is again a fraction of a meter. I'm not going to put meters since it's a fraction of a meter. 2.2 times 10 to the -2 of a meter. Now, next I'm going to order these numbers, and probably the best thing to do is, since these numbers aren't so big, is to convert them all to standard form so that we can really see what they are. So 5.3 times 10 to the 5th, so that's going to mean moving the decimal on 5.3 1, 2, 3, 4, 5 places to the right. So that's 530. That's 530,000, and this number we already have is 520,000, and then we have 7.5 times 10 to the 4th, so we're taking 7.5, moving the decimal 1, 2, 3, 4 places, so that's 1, 2, 3, so that's 75,000. So that one becomes the smallest number, so we'll list these as 7.5 times 10 to the 4th. Then we're going to have 520,000. We'll put these in their original form. And then the last one is 5.3. The biggest one is 5.3. Times 10 to the 5th. And that would be our answer based on our evidence there. Now, then we're going to list these very small numbers from least to greatest. We might need to stack these. So 4.5 times 10 to the -4th. I'm going to put 4.5 here. I'm going to move my decimal 4 places that way and put zeros in those little slots. And so that number is 0.00045. All right, this next number is what it is. And then this one is 4.8. I'm going to slide this 5 places to the left. So 1, 2, 3, 4, and 5. Put zeros in all those little troughs. And so this number is 0.00048. If if I slide up and stack these numbers, the other one was 0.40000047. This other one only had 3 zeros though. 4, 5. So anyway, so this would be the smallest. We'll call this the first number. The first number would be the one that is furthest away from 0. So this would be the smallest. This is a little bigger because the 8 is bigger than the 7. And then since this has a 4 where these have zeros, since this has a 4 where these have zeros, this has to be the biggest number. And so that's how we'll order them. Let's go ahead and consider that to be our answer. All right, so the volume of 1 mole of oxygen the volume of 1 mole of oxygen atoms is about 1.736 times 10 to the negative fifth cubic meters. All right, so cubic meters like a big box. So it's a small fraction of that. The volume of 1.5 times 10 to the fourth moles of, find the volume of 1.5 times 10 to the fourth moles of oxygen. So that's a little confusing. So let's just use what I like to call surrogate numbers to just see what we need to do here. So let's say the volume of one atom of oxygen was 5 cubic meters. And let's say we had 10 atoms. Well, if we wanted to find the volume of 10 atoms, we would just say 10 times the volume of one atom, or 50. So we need to multiply here. So we're going to multiply 1.736 times 10 to the negative fifth times 1.5 times 10 to the fourth. All right. So in terms of doing this multiplication, what we can realize here is that you just really have 4 numbers. You can break these numbers in scientific notation down and just think that what we really have is just 4 numbers being multiplied here. So we can multiply the powers of 10 and the non-powers of 10, and then that'll have us an answer in scientific notation if we leave it like that. So I'm going to multiply 1.736 times 1.5, and I'm going to multiply 10 to the negative fifth times 10 to the fourth. Now we know what 10 to the negative, if we add those exponents, negative 5 plus 4 is 10 to the negative first. And again, now I've got to do a little work up here. I've got to multiply 1.736 by 1.5. I'm going to turn this off for a second and just do that math, and I'll turn it back on and you'll see the result. So I did that up above, and I got that equaled 2.604 times 10 to the negative first cubic meters. So that's the answer to that problem. Now let's just do some basic multiplying just like that last problem. Let's just talk about how we do that, just get some fundamentals down. So again, what I'm going to do when I multiply numbers in scientific notation, I'm simply going to multiply the mantisses, or the number that's multiplied by the power of 10, and I'll multiply the powers of 10 separately. That's how we handle that. So 2 times 2.5 is 5, and 10 to the third times 10 to the fifth is 10 to the eighth, and there we have it. Pretty nifty, huh? Now down here we'll go 1.5 times 4, and 10 to the negative second times 10 to the negative fourth. Remember, we're going to add those exponents. So 1.5 times 4 is 6, and you add the exponents and you get 10 to the negative sixth, and that's all there is to it with that. And that's the end of the lesson.